Today's the 8th. Completely unexciting set of numbers for the date, 2/8/23. Again, I don't know what to call this. It's so random. I think, what was yesterday's notes? I think it was more log stuff.
Yeah.
We'll call today's like even more log stuff. More, is that what I called it? More with, I don't know. Is that what it was? Well, today's even more log stuff. So call it whatever you want, but it's just sort of, I keep just bringing up these topics as it's sort of organic, like in the moment when it's time to talk about it. Then I go, nope, we better talk about it. So today we have to talk about one property of logs, and this will turn out to be when we put logs to use, probably in the next unit. It might be later in this unit if you call it that, but we're going to do like word problems with compound interest and exponential growth and decay. This next property that I'm going to show you will be the one that you use the most. Ask any math teacher, and for practical purposes, this property is far and away the most useful. All right? So having said that, make sure you, well, I got to pause this because I got to change my attendance and I got to answer the phone. And oh, hello? Yeah. Yes, he did. No, I forgot to change the attendance. It's up to you. So as I was saying, there's a property that we have to talk about today. And this property, I say, will turn out to be the one, mark my words, that if you take more math classes, not all of you will, but if you do, and you continue on, this will be the one that just continues to pop up that you go, I'm really glad I know that property. So this property is fantastic. And what it enables us to do is it enables us to take a log with an exponent and move that exponent down and around. And you may not appreciate its usefulness yet. At no point today will you appreciate its usefulness. But when the word problems come storming in and we start talking about compound interest, these kind of stuff, then you're going to go, oh yeah, that's super awesome. So here's how it works. If I have a logarithm, and it can have any base, it doesn't matter. So I'm not going to put a base just like I did in yesterday's notes. So if I had, say, a log of a, and a is raised to the power of x. Again, you're going to think, well, that's not very cool. And I understand. It's not very cool. Useful, though. We can take that x and we can move it down in front of a logarithm and bring it down so it's no longer a power, but a multiplier. So to say that I have a log of a to the x is the same as saying x times the log of a. Obviously, this only works with logarithms, right? It's like pure black magic. But it also works the other way, which is the one that you're going to need to utilize today. So if I have a multiplier in front, like x, and it's being multiplied by the log of a, conversely, then I can rewrite this as the log of a to the x. Again, I know, seemingly useless and like, wow, what was all the hype about? It's not very exciting, but super powerful. So having said that, let's say that we're working through an equation today and we get something like 3 times the log of 4. Anyone want to take a stab at what that's equivalent to? So log of 64. Well played, Brooklyn. So this is something that's mandatory because the properties of logs that we want to use that we learned yesterday, you know how we can condense 2 logs into 1? You can't do that until the logs don't have coefficients. So like, for example, let me show you what I mean by this. Let's say you had 2 log base 8 of 3 plus 3 log base 8 of 4. Might get some bigger numbers than I wanted to here. But like at this point, yesterday's practice should make you want to condense these logs. Is that about right? That should be kind of in your system now where you think I can put those together, but you can't put them together yet because of the 2 and the 3 that are out in front. So what we're going to do is we're going to utilize that new power property of logs, and we're going to take the 2 and we're going to shift him up here into his new role and take the 3 and shift him up here into his new role. And we're going to get on this one log base 8 of what? 9. And on this one, we're going to get log base 8 of what? Very good. And now you can use your condensing property because the logs no longer have multipliers in front of them. So at this point, you could condense into log base 8 of 576. Got it? So that in its current state and in this usefulness in these terms, it's really only a little 5-minute sort of let's talk about it and move on kind of thing. But I wanted you to know that that's a legit thing. And you're going to start seeing that today. It doesn't pop up on every problem, but when you see it, make sure you get those multipliers from the front and stick them up onto the argument as exponents and then proceed like you did yesterday. So I have 2 examples for you. That's all. And then we're going to get crack-a-lacking on some work today. So I want to do these in a very correct order. So let's do this one first. Yeah, we're getting to the point now where we've, I mean, I still will probably tomorrow think of something else and go, oh yeah, I forgot about that. Oh, but really we're nearing like saturation at this point. Like as far as what we need to be able to do with logarithms, we're reaching sort of the peak of the mountain at this point. Like we got it all. We've acquired all the skills on our way to the peak. But this is weird, right? The base of the logarithm is a variable value. The argument of the logarithm is a variable value. So let's take a look at what this entails. It's not as bad as you think. So first off, there's no number here where the red arrow is pointing, so we don't have to use the new property we just learned today. And there are not multiple logs, so we don't have to condense. And there is not a log on the right-hand side. So at this point, instinctively, what should be our next step? Okay. Do the cycle, right? You guys both kind of said the same thing. Do that little cycle conversion. That's really our only option, is to get in there and put this into some language that we can work with. And so we're going to do the water cycle thing, and we're going to say x plus 5, u, sir, when raised to the power of 2 are equal to that. So it's going to look like this. X plus 5 squared equals 2x squared plus 8x plus 1. You warmed my heart. You got the square multiply double. I was a little nervous, but you did it. You set a good tone for us for the rest of the day. Yeah, remember x plus 5 squared on the left is a square multiply double. So great job there, Patzer. We have x squared plus 10x plus 25 equals 2x squared plus 8x plus 1. Quadratics, if you haven't figured this out, are pretty important, right? I mean, they just keep popping up, and we got to be good at messing with them, solving them. So which side makes more sense to pull all of our stuff to? Definitely the right. So we're going to wind up, if we take away x squared over here with x squared, take away 10x, we get minus 2x. Take away 25, we get minus 24. And we're back in a pretty familiar zone here. Just factor it. So there's a couple of rules that we're going to add to our notes, and I'm going to add them here in about a minute when we're done. That there's a couple little things. I spent a lot of time on the internet today, this morning, like 5 o'clock, trying to come up with good explanations for you. And I'm going to probably defer at least for one day, because I'm not comfortable explaining why a rule is a rule. If you asked, I don't want to give you my C game. Like I want to spend some more time coming up with some ironclad reasons for you. But just be it known. Let's solve this. Let's factor this, and then I'll tell you the rules that make one of the answers not work. So I think it's obvious it factors into x minus 6 and x plus 4, right? What then are my answer candidates? Mm-hmm. Good. So at this point in time, what we want to do now is we want to go back and we want to take a look at what happens if we put those numbers in. And this is the part that's a little bit uncomfortable. But if you go back to the beginning, let's say we put 6 in here. So we can check both of these. If I take 6 and I put it right here, that's going to make this now say log base 11. Good, good. And then I need your help. It is basic math at the end of the day, but I still would like your help. If you put 6 right there, what is 6 squared? What's 2 times 36? So I have 72. And then if you put 6 right here, what do you get? You get 48. And then if you add those, you get 120 plus 1 is 121. Is that a true statement? Yep. It is true. So 6 is a valid solution. Okie dokie. Okay. Let's see if our other answer, which I believe was -4, right? Does -4 work? And I'm going to try my best. Again, if this, I've already given the disclaimer, if my attempt at explaining this goes bad, then I'll defer a better explanation to another day out of respect for you. But here comes what happens, and I hope you see why this can't work. Fingers crossed. Here we go. If we try -4, so remember, one of my answers is -4, or I think it's a candidate at this point in time. So if I took -4 and I put it right here where this yellow arrow is, what is -4 plus 5? It is 1. And I have a couple things I want you to add to your notes today. And one of them is this. Ready? Have I lulled you to sleep? Wake back up. Logarithms cannot have a base of 1. And I would hope that you would understand why that is. And it's because a logarithm with a base of 1 doesn't make any sense. You know, if I said to you, log base 1 of blah, blah, blah equals 2. And this is the part where I just know this isn't going to go well. It's not a continuous sort of idea. It only works essentially one way. And that is if what's in here equals 1. For that reason, and that's I looked at like 40 different websites trying to find the right words that I could spit back out to you, and I left and just went, no, I'm not quite ready to talk about this. So what I meant to say to you today is this: a logarithm with a base of 1 is not allowed. So if that happens to you, you have to discount that answer. You have to cross it out as if it were one of the ones that makes one of our other illegalities occur, like saying log of -4 or log of 0, stuff like that. We're trying to now learn along the way, what are we and what are we not allowed to have? And you can add now to your list of no-nos, logs with a base of 1, no bueno. Right? I mean, think about like if I gave you log base 1 of 14, what's the answer? So you're telling me that 1 to the 14th is 1 or 14? It's not true, is it? So you understand that that's why a log of 1 can't work, is we'll find ourselves almost in every instance in a situation where I can't evaluate the expression. Right? Literally the only time it would make any sense is log base 1 of 1. What does that equal? 1. And the redundancy and oddness of all of that is why mathematicians have just decided logs with a base of 1 don't make sense. No bueno. So that's why yes, and that's why I'm not prepared to talk with, because I knew that you were going to be the person to bring that up. Good on you. Yes, in this case, if you put -4 in here, check this out. Go where my yellow arrows are at, right here and right here. What is -4 squared? Yes, and 16 times 2 is 32, and 32 minus 32 is 0 plus 1 is 1. So we have found the one instance in which it's true, but by definition, a log of 1 is not allowed. Right. As soon as you found an answer that makes this base equal 1, then you can cross that one off and not even worry about whether or not the rest of it makes sense. Is that acceptable for now? Terribly unacceptable, but acceptable. So I want you to add into your notes that logs cannot have a base of 1. Can you think of something else that a log can't have a base of? Very good. And that's the one that I literally cannot explain to you yet. I'm not even going to clumsily try, so don't ask. But I can tell you, because I did find, kind of like with this one, exceptions to the rule. But I think what, again, it is just a bailout. Mathematician said, if it doesn't work, let's make it never work. So logs cannot have a negative base either. And what's one other thing that a logarithm cannot have a base of? Very good, you guys. That was a good team effort. So let's add these into our notes and make sure that come quiz day, if you need it, that you add this on in a little corner of your page of notes. So logs can't have base 1. They can't have base that's negative. They cannot have base 0. All right, was that example okay for you then? So we accept that x just equals 6 and x cannot equal -4. All right, let's do one more, and then I'm done, and then you can work. And I'll probably give you the rest of the hour, but I'll probably also give you tomorrow too. And I shouldn't have any new content for you tomorrow, which is good. So we have a log with a base of 3x minus 1. The argument of the log is -9x plus 21, and it equals 2. So I know that last example, when I put it up, it kind of freaked you out a little bit, the whole variable and the base thing, but now you're kind of like, okay, I can cycle this out. And so if I convert it over to an exponential, what will I get? 9x squared minus 6x plus 1 equals -9x plus 21. And I know in every room there's always someone who's like, how did you get that? But they either are too afraid to ask or just too not wanting to ask or something like that. So the question might in your mind be, where did this come from? For God's sake, where did that come from? And remember, that is just this thing I'm circling in red raised to the power of 2. So it's that square multiply double rearing its head yet again. 3x squared is 9x squared. -1 squared is 1. Multiply them together, you get -3x. Double it, you get -6x. So good. And then, of course, we're just back in Quadraticville. Let's just move all your stuff to one side. Clearly, we want the left, so we're going to leave 9x squared. We're going to add 9x to get plus 3x, and then we're going to subtract 20 to get -20, and then we're going to set it equal to 0. So just be prepared, not all factoring is warm and fuzzy. Like that last factoring was like, meh, put me to sleep, but this is a little bit tougher. So I'm going to try this combo. Sadie, this is your favorite thing, I know, factoring. It's your bestie, right? This is your favorite, right, factoring? She loves it. So if I try my 3x's, tell me about my signs. For sure, 1 plus 1 minus, and I'm thinking a 4 and a 5 maybe. Put a 5 on the beefier one and a 4 with the negative there. I like that. 15, -12. That works. So what are our answers? So yet again, we want to take a quick moment and go back and see what's what. And so we're going to find ourselves again in a position where, like, it was super clumsy, but that last little conversation we had about the weird base being 1 thing, again, our focus isn't going to become so much, does the mathematics actually check out, as does something bad happen with the base, or does something bad happen with the argument? So let's check it out. So let's try -5/3 first of all. Let's take those answers and give them a check. Yes, and so I'm just kind of move this up. Sorry, it's a little clumsy, but there, now we can see it. So if I take negative 5/3 and I put it right in here where this little yellow arrow is, can we all agree that a positive 3 times a negative 5/3 is something negative? And then when you take away 1, it just gets more negative. And as per the third rule we talked about, or the second rule perhaps, that's not okay. So we're going to need to just cross out negative 5/3 without any more fanfare, just kick it to the curb. All right, and let's take 4/3 real quick for a spin and make sure that only good things happen. So if I take 4/3 and I put it where the little yellow arrow is, I need your help with your basics here. What is 3 times 4/3? Yeah, it's 4, right? Yeah, the 3's cancel, so it's just 4. And then 4 minus 1 is 3. So we have a base of 3, so we're all good there. And then if you take 4/3, follow this long green arrow and put it right here. What's negative 9 times 4/3? Yeah, negative 12. We're good to go. So that's that. But plus 21, so it comes out positive, right? Sorry, that was a little longer, but you know that's generally how I roll. So it's like 25 minutes, my bad. Good. I know some of you maybe are a little bit overwhelmed, and some of you are on the dead opposite end of the spectrum. Like I've got the full gamut right now. Some people are already done with all the work, and some people are still mugging around on the early ones. So please, no shenanigans, none of this phone stuff, none of this silly nonsense. Get your work done, okay? All right, cool.